morning. If everybody could please take their seats, would be greatly appreciated, and we can get started here in a minute or two. Okay, good morning and welcome. My name is Mike Smithson. I'm a Senior Vice President with Skanska, and I'm the chair of the conference for this year. For the first time in 19 years, the United States is hosting the WTC, and we're very proud of that. We're glad to have it back. It's been a long time coming, and thank you to the ITA, thank you to the member nations for allowing us to host this wonderful event. This Congress is going to provide you with an outstanding technical program that connects you with tunnel professionals from all around the world and offers you an insider's perspective of the projects we design and build. A little bit about our host city. San Francisco is often called everybody's favorite city. It's a title earned by its scenic beauty, its cultural attractions, its diverse communities, and world-class cuisine. Measuring 49 square miles, this very walkable city is dotted with landmarks like the Golden Gate Bridge, cable cars, Alcatraz, and the largest Chinatown in the United States. A stroll of this city's streets can lead to Union Square, the Italian-flavored North Beach, Fisherman's Wharf, the Castro, Japantown, and the Mission District. The city has a colorful past, growing from a small village to a major city following the 1849 gold rush. It truly is. It's got a diverse community. People are friendly. Go out, walk around. It's a very walkable city. I encourage you all to take the time to do that. We'd like to begin our day. At Skanska, we always start with a safety and an ethics moment. I'm going to pick two simple topics here for a Congress or a conference of this nature. Number one is emergency exits. Know where your emergency exits are. We have them in the back of the room and the side doors. If anything should happen, the alarm goes off, please get up calmly and walk orderly outside and up the escalators and out of the building. It's easy to get yourself turned around. We're underground at Moscone Center here. It's a beautiful conference facility. You're going to be in different rooms all the time. When you walk in, always do that. Another important thing is most of us come here with colleagues and friends. Pick a muster point. Pick a gathering place that if there is an emergency, there's a park immediately behind us between the Marriott Marquis, which is the host hotel, and this conference center. Pick a place. Get the phone numbers of your colleagues and friends. And if anything happens, keep track of each other, okay? From an ethics moment, this is also a common topic whenever we attend these type of functions. Many of us work for designers or contractors, or if we're in academics, we're consulting or working on DRBs or different things. We interact with the owners, interact with the contractors, and interact with the designers. Somewhat unique to our industry, we're oftentimes partners on these jobs, and other times we're competitors. So be very cautious. Don't talk about bidding when you're talking about bidding or pursuit of work or disputes within your work. If you're not sure who's in the audience and you're not talking to your close group, have the conversation later. So again, safety and ethics should be at the forefront of what we do, and just make sure that you try to pay attention to those simple rules. Following the welcoming comments, Art Silber will be up here after me, who's the chairman of the UCA of SME. We'll have the Muir Wood lecture, Ground Support for Deep Underground Construction, Challenges Managing Highly Stressed Ground and Civil and Mining Projects from Peter Kaiser. He's a professor emeritus from Laurentian University in Sudbury, Ontario. Following that, we'll have a refreshment break from 10 to 10:30. We'll have coffee outside and probably a little bit of food. We'll be welcomed back in by the University of California Band, so we'll get to hear that. And then following that, we'll have two keynote speakers. One, Peter Grucock, former CEO of the Kiewit Company, followed by Peter Hirschberg. So they'll talk about our industry and about innovation and how to incorporate innovation into city planning and city building. I'd also like to take a moment to thank and acknowledge the tremendous support of the 2016 WTC and ITA for their sponsors. Without these companies, we could not have brought you this Congress, especially the ITA prime sponsors. You know, they carry the load for ITA across the world, and they should be recognized. They're up here on the board, and if you see members from those companies, please tell them thank you. In addition to the prime sponsors, we also have the conference sponsors. We have the gold sponsors, silver, and bronze. So the gold sponsors you see up there, silver sponsors, and these are all also acknowledged in your pamphlet in your Congress proceedings. But again, we thank these sponsors. It's a commitment to the industry. We have a strong industry, and it's because of companies like this and the people that work with them. In addition, I'd like to personally thank all the volunteers. For all of these conferences, they're largely put on by the volunteer efforts. I know Art Silber's going to thank personally some of the ones that were on this organizing committee, but all of these conferences deserve, the people really do deserve a round of applause. They put in tireless hours. It takes a lot of effort. And we'd also like to thank the companies that support their employees in doing this. It's not always easy to send our people around the world or around the country to have these meetings. So we would like to thank the companies as well. And now I'd like to introduce you to Arthur Silber. He's the chair of the UCA of SME.
Good morning and welcome. On behalf of the Underground Construction Association, I'd like to again welcome all of you to San Francisco. I'm Artie Silber, the chair of the executive board of the UCA and also senior vice president of Mott MacDonald. The Underground Construction Association is an industry association of engineers, contractors, owners, government agents, and others with professional interest in the underground construction industry. The purpose of the UCA is to provide professional development, technical information, and networking opportunities to members tackling some of the greatest challenges in the underground construction and tunneling industry. The UCA of SME provides current insight on the latest technologies for underground tunneling and excavation, state of the practice for tunnel and shaft construction, effective project planning, cost estimating, project design and delivery, overcoming challenges of challenging site conditions and constraints. Another very important and primary goal of the UCA of SME is to fund and perpetuate a scholarship fund for the development and training of new engineers for the industry. This year, the UCA has awarded 4 scholarships of $5,000 each and participation at this meeting. As I read the name of each of the 4 recipients, I would ask them to stand and be recognized. Please hold your applause until all 4 names have been read. Adam Reinbold, Maxwell Engen, Michael Kennedy, Yuan Lee Wu, the UCA of SME young members also had the opportunity to give 43 students a scholarship to attend WTC 2016. If you are one of the 43 students who received this scholarship, please stand. Join me and congratulate these students. Considerable volunteer time went into developing this Congress. To that end, I would ask that each member of the organizing committee stand as I call their name so we may recognize their considerable and unbounded efforts. Please hold your applause until all are standing. Tom Clemens, William Edgerton, Amanda Elioff, Randy Essex, Bill Hansmeyer, Locke Home, Allan Howard, Leon Jacobs, David Klug, Mike Mooney, Priscilla Nelson, Mike Rispin, Jim Rush, Henry Russell, Mike Smithson, and Olivier Vian. I'd also like to mention that a considerable effort by many volunteers of UCA organization put together a history of tunneling book in the United States, which is a 500-page book that will be sent to each registrant of the Congress. You will get those shortly after the Congress has ended, and they will be provided to you. In addition, additional copies will be for sale and can be procured through the UCA of SME website. Next, I would also like to thank all of the UCA staff that put this together with considerable effort, working many nights, many weekends, and long and hard, tedious work here. So to the UCA staff, my personal thanks to each of you also. Another important thing is that from the many past Congresses, we have learned many lessons and have tried to incorporate those lessons into this Congress to provide you with the utmost Congress here that we could provide to you. And we are also willing to provide our input to any future member nation for future WTCs. So please contact us at any time, any of the future nations. With that, I would also now like to introduce the ITA President, Soren Eskesen.
Good morning. Thanks, Allan, for the introduction. And dear WTC attendees, dear colleagues, and dear friends, let me just introduce. I'm Søren Eskesen, the president of ITA, and it's getting towards my end of my term with this conference for 3 years, and I decided I'd also work with the COVID as for the design. But I would like to welcome you all here to San Francisco, and I actually will congratulate all of you. You made an excellent choice when you decided to join us here at the ITA World Tunnel Congress 2016. I dare to say that you are joining us here at the most important event within the global tunneling industry in 2016 being this ITA World Tunneling Congress. And this year the topic is uniting the industry, and we do this by gathering the whole ITA family for networking and exchange of knowledge here in sunny California, at least outside sunny. It's the Underground Construction Association of SME who is organizing the conferences. And with several hundred of unique technical presentations, short courses and breakout sessions, you have a chance to learn from the experience all around the world. And with the 300 exhibitors representing all types of products and services of the underground construction industry, you will also be able to network with colleagues and peers within our industry and to exchange knowledge and learn about the recent developments. Also during the conference, the ITA working groups and committees will meet to continue their important work in preparing reports and best practice to share within our industry and with our members. The working groups and committee are the backbone of ITA, and their work has for more than 40 years contributed to the recognition of ITA as the world leader in tunneling. The ITA open session tomorrow morning, Tuesday, is devoted to the work of the ITA working groups and committees. Here you will be able to learn about the functioning and the activities of the working group and committees, and to get a first-hand knowledge of the latest ITA reports and developments. The ITA open session is organized in a form that will invite to discussion and input from the audience. So please join us and participate actively in the discussion. In the past year, we have seen the successful completion of many important projects like the Lake Mead and the 2nd Avenue Tunnel in New York, and also other important projects around the world. In order to recognize the success of our industry, ITA has initiated the ITA Tunneling Award, and we in November 2015 successfully held the Tunneling Award 2015 in Hagerbach, Switzerland, and we received 110 entries from all around the world, showing the successful project and technical initiative that has been done during the year. We organized it as a one-day conferences where these outstanding achievements could share, the finalists could share their knowledge and experience with all of us by explaining how they did and what they did. And then in the evening there was a gala dinner where the winners received a Brunel statue as a recognition of their contributions to our industry. And following on from the 2015 awards, we have decided to hold the 2016 ITA Tunneling Awards in Singapore on the 10th and 11th of November this year, and we encourage you already now during this conference to identify entries that you can make to the awards and also register for the conference. The registration is open on the web page, both for making entries and registrations. All around the world, there is a continuous increase in the need for new tunnels and use of the underground space. And this is driven by the benefit these tunnels and the underground structures offers to our societies. Tunnels provide water to our cities. Tunnels take care of the sewers and thereby keep our lakes clean. Tunnels are an integrated part of hydropower projects, and they therefore help providing sustainable energy to our cities' ever-increasing needs for energy. Tunnels are also used for flood control and thereby helps reducing the impact of the climate change. Tunnels reduce traffic congestions in our cities and thereby also help reducing the CO2 emissions. Tunnels and underground structures help our cities to become resilient by transforming surface problems into underground solutions and thereby improve the quality of life for the inhabitants. So what we do as tunnelers are important for our societies. Let us therefore all work to fulfill the theme of the Congress, Unite the Industry. As individuals, we may be excellent, but together we will be outstanding. With the increasing urbanization and increasing growth of the world's populations, our cities and society needs our industry's service in transforming the surface problem to underground solution. There is a big need for our industry and our services out there, and from what I can see, our industry has a bright future ahead. Finally, I would like to thank and congratulate UCA of FME for all the hard work and the arrangement they have done to make this year's WTC a remembered one, and I wish you all a successful conference, and I hope that you will leave San Francisco with new input, new knowledge, new friends, and more wise than when you arrived here. So welcome to the WTC and welcome to San Francisco. Thank you. It is now my pleasure to call upon the ITZ Foundation, who will hand out some awards, and I will call upon Felix Arnberg and Per-Georg Ubrasso to join me.
Good morning, everybody. Per-Georg Ubrasso, as Vice President of the Council of the ITZ Foundation, and myself as Secretary of that same Council, feel honored to hand over in this venue this year ITZ Foundation Award in order to acknowledge outstanding achievements and contributions to the goals of the ITZ Foundation. This award goes both to an organization and a person who have contributed in that sense in the development of the foundation. I feel honored to hand over the this year ITZ Foundation Award to the Mexican Association of Tunnels, AMITOS, in recognition of their activities, which it has developed over the last 3 years in close collaboration with the ITZ Foundation. AMITOS has organized in the last 3 years regular training courses, and it will also do the same this year in October, in particular on soft soils. AMITOS did that recognizing that there is a need for training and education of their engineers, of their graduates, of the industry, in favor to enhance the Mexican tunnel industry. ITZ Foundation as such felt honored to support and collaborate AMITOS to achieve this target. And we are more than happy to see that they not only organize courses, but they also will introduce a postgraduate master course, which is just the next step in pursuing the aim of delivering training and education for the Mexican tunnel industry. And I now would like to ask Roberto and Francisco to join me on the stage to receive this award. And I ask you to acknowledge these achievements with an applause. Thank you.
Good morning to everyone. I would like to express some words. Dear President of ATA, Mr. Søren Eskensen, members of the Executive Council, ITASET Foundation, member nation of our association, ladies and gentlemen. On behalf of AMITOS, the Mexican Tunneling Association, I would like to thank you for this important recognition, which I'm honored to receive in their behalf. I would like to mention and acknowledge the work of lots of people back in our country that have helped us as a team to achieve these merits that today we account for. Always having in mind the mission statement of the underground construction. I would like to thank Claude Beringer, with whom we started this project since Vancouver, a great WTC. Thank you, Francisco Suarez Fino, as previous president of AMITOS, to always support the cause and to give importance and follow up on everything that was needed in ATA and ITASET projects. To yourself and Andres Moreno Fernandez, among many others, for the effort involved on the creation of the master course, now a reality for our young engineers, which are proud now to have it in AMITOS. Also, the young member group in Mexico as an active organization. Lastly, I would like to mention that as president of the term 2015-2017 plus, I would like to increase our participation with ATA and go hand in hand in many more projects as possible. We firmly believe that promoting to go underground is the only way to go, especially for a complicated megalopolis that has so many issues as Mexico City. There is no other way but to keep fighting from our trenches to be able to change people's mind and make them realize that as well. Thanks again for this great award, and enjoy a great World Tunneling Congress. Thank you.
As a vice president of the foundation, I'm really proud to invite Allan Wagner for the personal recognition and the award we are giving to him for his extremely important support since the beginning of the foundation. He graduated in Graz and PhD in Hamburg in geotechnics, and since the middle of the 70s, he worked a lot as a planner, designer, consultant, but especially as innovator in our industry, developing both in conventional and in mechanized tunneling brilliant solutions. The States, North America, Europe, Japan, and quite everywhere. But what is important, in the last 2 decades, he started with serving ITA as a member of the board, and then vice president in the terms 2004-2007, and then immediately started with the idea of the foundation, supporting the development and serving as a professor, as a lecturer, everywhere with a very impressive dedication and success. May I give you this recognition?
Well, I would like to say just a few words, unprepared as I did prepare. Number one, I'm deeply honored and deeply pleased to have received this award, totally unexpected also. Second, I would like to thank everybody, in particular Claude Berenguer, who is kind of a spiritual link with me, as well as ITA President Søren Espersen, which I have been known for 20, 30 years or so. And I would like just to leave one message to you. This is the message why I did try to contribute to the wonderful family of ITA. And there's only one reason for that. I have big fun working with ITA, and I would like to share that. And if you have fun, you can overcome many, many obstacles. You will always be successful. So this spirit I would like to give, in particular to the young engineers. And with that, I would like to thank you all for your recognition of this award. Thank you very much.
Yeah. So, congratulations to both recipients of the Foundation's awards, and then on to my next duty is to talk about the Muir Wood lecture. We will have the Muir Wood lecture presented by Dr. Peter Kaiser. But before I do that, I would just say that we in ITA introduced the Muir Wood lecture, both in order to honor Sir Allan Muir Wood, who was our first ITA president, and also to share the spirit of Sir Allan Muir Wood. And then the objective of the Muir Wood lecture is that it should be visionary, it should be open-minded, open to take new input in, and it should look for future trends in the tunneling technology. The present of the Muir Wood lecture is decided by the Executive Council based upon suggestions from the ITA members. And before I introduce this year's Muir Wood lecture, I would have a pleasure to announce that the Executive Council on its meeting here in San Francisco on Saturday decided that the Muir Wood lecture for 2017 will be held by Professor Håkan Stille from Sweden. So congratulations to Professor Stille, and we will look forward to having him on the stage next year. But But now it is my honor to introduce the Muir Wood lecture for 2016, which is Professor Dr. Peter Kaiser. Peter Kaiser is a graduate from the Federal Institute of Technology in Zurich, in Switzerland, and the University of Alberta in Edmonton, in Canada. Since 1987 and until his recent retirement, he was a professor and chair for the rock engineering and ground control in the Barty School of Engineering of Laurentian University in Sudbury, in Canada. In 2000, he was seconded to the Center for Excellence in Mining Innovation as a founding director, and then as a director in Rio Tinto Center for Underground Mine Construction. And he also holds an adjunct professorship at the University of Waterloo in Canada. So he will today speak to us about ground support for deep underground constructions, challenges of managing highly stressed ground in civil and mining projects, a topic relevant for many of us. So, Peter, can I welcome you here?
Good morning, ladies and gentlemen, and thank you for your kind introduction. It is clearly an honor to be selected to present the Sir Muir Wood lecture, and it is a pleasure to talk to you today about the topic of ground support for constructability in deep underground construction. Before I may confuse you by the content of the lectures, the facts and figures that I present, the message of my talk today is very simple. If a project is to succeed, it has to be designed so it can be built. And that's what is reflected in the term constructability. By indicating in the corners of the slides the logos of various institutions, I simply like to point out that much of what I have to tell you today came from work at these institutions, Laurentian University, America, that I was leading for a while, and the Center of Excellence in Mining Innovation was Rio Tinto-funded Center for Underground Construction. As was just said, the lecture series was created to keep the spirit, the vision of Sir Allan alive, and to push for innovation for economic and safe construction in tunneling situations where uncertainty is part of the problem. Previous lectures have dealt with issues of hydrotunneling, large tunnel projects or large tunneling projects, machine tunneling, subaqueous tunneling, and tunnel face stability. I've chosen to talk to you today about challenges of managing highly stressed rock in brittle failure modes for both civil and mining projects, simply because I have seen that many projects are suffering problems in these conditions, and innovation, as in the left image, is needed to deal with strain bursting condition. And if we're getting out of control in mining, we have serious instability problems that have to be mastered by better understanding what the rock is doing and what the support has to do. Having just spent the week in Yosemite Park, I couldn't resist to put this slide in to indicate that I have a very narrow focus. I will address this topic from a rock mechanics perspective, and also to indicate that there is no challenge too high that it cannot be overcome when we have the right know-how and the right skills. You may not see the little guy in the image climbing the cliff of 4,000 feet. It takes a climber typically 2 days with 2 overnight stands. This individual can climb it in less than 5 hours, 4,000 feet vertical. I was always inspired during my research by Sir Allan's writings, his books, etc. Unfortunately, I never had the pleasure to work with him or to meet him. But one motion that he presented at the British Tunneling Society reflects the content of the message that I have today. Tunneling contracts are best implemented based on a detailed design procured by the client before tendering the construction contract. Robust engineering, independent of whether the engineer or the contractor is responsible for the design, has to take into account the complexity and variability of the geology, has to consider aspects of construction so it can be built efficiently, safe, and with effective support system, and for that purpose it is necessary to properly describe and anticipate the rock behavior as well as the excavation behavior. In my experience, many problems that we have encountered in deep construction come from the fact that the behavior was not properly anticipated, not described, and as a result, the efficiency of the construction process was hampered. Dr. Hook, in his online lecture on the art of tunneling, uses this matrix to describe what are the failure modes that we can anticipate in tunneling, characterized by the stress level on the vertical axis and the rock mass quality or strength on the horizontal axis, basically describing the whole spectrum of tunnel behavior from essentially elastic to squeezing condition in the lower right. Terzaghi in the mid-1950s was the first to try and quantify how different rock classes, and I know you cannot read the details, but he used the different classes to describe what the rock load on steel sets should be, and therefore assist to link the geology, the ground condition, to the tunnel behavior and the support requirement. All the rating systems that we use today, Q, RMR, and in our case GSI, to get numbers for rock support design or for the determination of the strength, are basically built on those early steps. I had the pleasure to work with Dr. Hook to establish the GSI system, and as you can see on the left side here, one axis is basically built on the rock classes that Terzaghi had identified, the blockiness on the rock mass. It is then combined with the joint conditions that make up the blocks, and in this way it is possible to assign a number to a certain rock condition, and you see 4 examples from reasonably good quality rock to poor quality rock. GSI is not an accurate number, it's not a magic number, but it gives us the ability to assign numbers or ranges to the rock quality that is needed to identify what the anticipated failure modes could be. On the vertical axis, we have the stress conditions. That is typically described by the overburden, and as I will explain later, that unfortunately leads to many problems. It is much more appropriate, as is shown on the right side, to define the stress level by the maximum tangential stress around an excavation that can be simply calculated from the principal stress values and from the stress ratio. I'll come back to this later, but by the hatched areas, I'm indicating that my talk today is focused on these 5 rock classes, not when structurally controlled failure dominates or when we have squeezing or swelling conditions. Just 2 examples to illustrate what I'm talking about. This is a tunnel that many of you, I'm sure, have heard about, the Niagara Tunnel, where we ended up with some instability problem, severe instability problem as shown here because of high horizontal stresses causing failure in the roof. And you can see here that the contractor realized the problem and tried to overcome the issues by some supplemental support. The point I like to make here is that this type of condition was not anticipated at the tender stage and therefore led to serious safety as well as production issues. The second example from the Gotthard Tunnel shows here that we have stress fractured rock emerging from the TBM shield, finger shield. You see the stress fractures in individual blocks, and the consequence is that we have what I call raining rock behind the finger shield. And when the support system that was designed with U-profiles had to be installed, we end up with flying arches that are not in contact with the rock and therefore certainly do not immediately function as a support system. So when we have these kind of situations, we have to ask ourselves, why do we have these kind of problems? What do we not understand? And in my view, most of these problems are related to the fact that the brittle failure process of the rock mass is not understood at the tender stage. And I'd like to explain to you why and how we can anticipate these type of conditions so that we don't have interruptions of the construction process. I've prepared a very detailed summary of my talk, and it will be handed out to you. I will focus on the anticipation of the rock mass behavior, at depth, and I will then try and summarize how that should impact the support design, what I call deformation-based support design, towards the end of the lecture. On the right here, you see an image of a rock mass that illustrates what I'm talking about, a rock mass that is stress-fractured and is falling apart into blocky rock of fragmented materials. The general process of designing from a geomechanics perspective a tunnel includes the various aspects that everybody's aware of: geology, data collection, drilling, laboratory testing, classification, leading to a preliminary selection of the support system as well as the excavation technique, then more sophisticated analysis numerically or use of empirical techniques to come up with something that we hand over to the contractor to build the tunnel. When we deal with brittle failure and stress fracturing, as I just indicated, we have a problem at the interface between numerical modeling as well as empirical methods and the determination of what the construction problems are. So how does brittle rock fail? I'm illustrating this here on a heterogeneous sample that is being loaded in the vertical direction, is confined with 2.5 MPa, more than any support can provide. And as you load this piece of rock up, you end up with a stress distribution that is not uniform. And as the dots indicate here, you end up with islands of tensile conditions in a rock mass that overall is confined, but locally is not confined. If we then go back to work by Griffiths and Hook and others in the early 1900s, and combine this with the fact that cracks propagate or fractures propagate easily as the confinement is reduced, we understand that spalling behavior, as is illustrated here, with parallel fractures to the excavation, must be expected whenever tensile or near tensile conditions are generated in the rock. This graph may not be familiar with too many of you, but I'm showing here the major principal stress against the confining pressure. And if we look at how much tensile condition is to be anticipated, we find that for a given stress level, there is less and less tension as the rock mass is confined. Or putting it the other way around, there is a limit, which we call the spalling limit, when we cannot confine the rock enough, or we do not confine it enough, and we have spalling behavior, as I just showed you in the previous slide. The practical relevance of this is that the rock mass strength that we anticipate using standard procedures is severely depressed in the low confinement area, so that we have, instead of a continuous failure envelope, we have an S-shaped or trilinear failure envelope. The major point being that the strength near the excavation in these rock types is about 50% or less of what we typically anticipate. For practice, this has a very important implication, and that is that to the left of this limit shown here at 10% of the UCS, unconfined compressive strength, we have spalling processes dominating, whereas to the right we have shear failure mechanism dominating. For the practice, it means that all the problems related to support selection, related to strain bursting, or other mechanisms, slaking mechanisms, swelling mechanisms when water penetrates through cracks, caving in mining, or fragmentation are dominated how the rock behaves in this depressed strength area, and not by what happens when we have good quality rock. Only when we have issues of pillar design would we be able to mobilize the full strength for the rock. So if I look at this a little bit more in detail, and I take an example of a UCS of 120, divide by 10, and I plot the confinement contours around a tunnel, you recognize that the inner shell, the zone where this spalling mechanism occurs, is relatively shallow maybe half of a tunnel radius in most situations. And if we go back to the example that I introduced earlier, was the raining rock and flying arches, you can now understand and see in the image that we have surface parallel fracturing that disintegrates a massive to moderately jointed gneiss and leads to a relatively shallow, maybe 1 meter deep, stress-fractured rock that terminates at discontinuities but is not controlled by the blockiness of the rock mass. It is controlled by the stress fracturing that happens right at the tunnel face in the finger shield. If we model this with a fracture code called Allan, we find something very interesting, and that is if the stress ratio is 0.5, meaning higher vertical than horizontal stress, we would only anticipate stress fracturing in the walls. However, if a rock has a relatively low tensile strength, the stress fracturing process is not following the conventionally known yield conditions. It involves the entire tunnel excavation surface, and as the model shows, we end up with surface parallel fracturing rather than radial fracturing. And it is this process of stress fracturing in low tensile strength rock that has plagued this project that I illustrated earlier. We collected a fairly extensive database to see whether we can establish an empirical relationship for the depths of failure, plotted this on a normalized depths of failure graph, and found that there is, when we take projects from around the world, more or less a linear relationship between the depths of failure and the stress level quantified here in terms of the tangential stress divided by the unconfined compressive strength. What is of practical relevance is that this process does not start when the stress around the excavation reaches the laboratory strength. It starts at 40% of the strength. Recently, Paris and Dietrich have done some work to illustrate that this relationship may not be perfectly linear, rather curved, but more importantly, they also have added knowledge to allow to determine what the mean depths of failure is around excavations. So the greatest depths of failure, if the stress level at the excavation boundary is equal to the strength of the rock, would be in the order of 70% of the tunnel radius, and the average or mean depths of failure along a project would be anticipated to be maybe 15% of the tunnel radius. The point here is, without boring you with the technical details, is that today we can anticipate brittle failure as well as the extent, and most exciting overall is that we can anticipate the percentage of problems that we have to might occur along a tunneling project. I superimpose a normal distribution, basically showing that 50% along this tunnel, it would be anticipated to have a depth of failure of 10%, only 5% of a severe, or maybe 1% even more severe condition, if in this case the rock mass, the stress was equal to 75% of the UCS. So in summary, for what I have talked about so far, we understand what the brittle failure process is. It is stress-driven. The stress failure can be predicted and quantified and properly described at the tender stage. And today, retroactively, it is well understood why we ended up with these situations that I illustrated earlier. So how do we quantify what is to be expected in a tunnel project? The situation is relatively simple because the stress level basically contains two aspects: the maximum stress around the excavation and the strength. Therefore, we need to establish the rock strength as well as the stress, and most importantly, the anticipated variability along a project. The details are described in the written note, but we basically use laboratory testing and rock classifications to arrive at rock mass properties that go into the design. The unfortunate thing is that both the Q, RMR, and other systems have not been calibrated on conditions with stress fracturing, including the GSI approach that I have introduced earlier. And in general, that means that in conditions where we have massive to moderately jointed rock and intermediate to high stress levels, the conventional or available systems fail to capture the brittle failure process, the disintegration due to stress. To illustrate this, let's look at some examples here where we start with a rock that is compact, massive, but due to stress, we have excavation instability modes that lead to relatively large, blocky materials, or to relatively small, slabby, disintegrated rock. The point is, from a tunneling perspective, we're not dealing with the nice, undisturbed rock. We're dealing with the degraded rock properties. And if we translate this knowledge into Bianowski's stand-up time chart, which has the stand-up time as a function of span and rock quality, we have to realize that our tunnels that we excavate are not in the virgin ground condition. They're dealing with the degraded rock. In terms of the GSI chart, that means we're not dealing with conditions of high GSI values, but lower GSI values, and therefore stand-up times that are not in the order of months, but they're in the order of a few hours. The only way to overcome these problems is by constructive measures, and if the construction techniques are not such that the stand-up time issue can be managed right at the face, you end up with delays and excessive costs because you have unraveling problems of the inner shell or raining rock, as I had introduced earlier. The second aspect is to determine the stress field so that we can better anticipate the depths of failure. Too many times I read in geotechnical reports that the state of stress is to be expected by assuming a linear trend with depths of overburden, and that the stress ratio can be assumed to be nearly unity. And I have to ask you, is this really the case? I use here a calibrated model for a Canadian shield of 2,000 meters of rock that is heterogeneous, that I tectonically strained to reflect the setting in the Canadian shield. And on the right side, you see a plot of the vertical stress, the minor horizontal stress, and the major horizontal stress. If you describe this by any linear trend, it is quite obvious that the input for the design is highly flawed and incorrect because we have variability in stress, particularly in horizontal stress, and maybe in vertical stress we have a linear trend, but certainly not for the other two stress conditions that dominate tunnel behavior, the horizontal stresses. As you can see in this figure, there is a linear trend at depths, but there is an intercept at the surface, which means the stress ratio, K, which is the ratio between the major and minor principal stress, is not constant with depth. It actually has a very high value near the surface, and by these black lines you see that when you introduce heterogeneity into a rock mass, this ratio varies widely. You also see on the graph measurements along a tunnel that reflect this high variability that the numerical model presents you. The conclusion is very simple, and that is, if a project is designed under the simplified assumption of linear stress with depths and a K-naught ratio near unity, you're far off the reality, which is that stress is highly variable in a heterogeneous rock mass along the project. And if you support this design for the simplistic assumption of K-naught 1, it likely is flawed and will not be adequate to solve for the problem with stress fractured ground. Earlier, I introduced the concept of depths of failure prediction, and for that we need the tangential stress around the excavation, which I have now calculated for this model, and we find some very interesting things. I have assumed that the tunnel is at different depth levels, and I've calculated the stresses, maximum stress in the wall and the maximum stress in the roof. They're very variable and changing with depth. The implications for a project are that you have various failure modes dominating at the surface. Low confinement or even tensile conditions in the wall and low confinements in the back leading to structurally controlled failure mechanisms. However, locally there can also be extreme stress concentrations, twice the stress that are encountered just before, and this leads to a combination of stress fracturing and joint interaction that then leads to the spalling type behavior that I have introduced earlier. As we go to greater depths, the failure mechanism changes, and interesting enough, the stress in the roof more or less is constant independent of the depths of the tunnel. It still is slightly variable, but as we go deeper and deeper, the stresses in the walls are increasing, and as a result of this, the failure mechanism around the excavation changes as the stress field changes. Here are two images to illustrate that. The top one showing stress fracture ground in a tunnel in the upper area where stress was dominating over the structure, and then at greater depths where the stress fracturing mechanism rotated to the side walls. And if you have a TBM, you can imagine the kind of practical problems you run into. In the written contribution, I have two case histories that are too complex to discuss here, but just in the image below, I show you how the overbreak varied on a tunneling project within 15 meters, and the rock was relatively uniform, but the stress was changing drastically. So we have overbreak in the back on one side, overbreak on the other side, and eventually overbreak including the entire circumference, even floor heave due to bulking of rock in the base. So in summary then, for this part, we have highly variable stress and rock conditions. If that is the case, we need to quantify both the variability in strength and strength, along stress and strength along a tunneling project, and then translate that into construction and support techniques that are amenable to this variability. Open shields cannot manage the rock that is stress fracturing right at the front easily, cannot provide face support. If you use steel sets or U-profiles, you have no support that is immediately interacting with the failing rock, and therefore only becomes effective once you shotcrete it in at a distance from the face. Scaling practices that often are used are not really helping stability. They only increase the overbreak and create difficulties with construction. So now that we understand what brittle failure means and what the consequences are for underground construction, I'd like to move to the ground control issue on how do we support this type of rock. Clearly, from what I have described so far, stand-up time issues have to be managed. The rock wants to ravel, it wants to fall apart, and immediate support is required to stop this process. But there is something else that is happening when you stress fracture a rock. Just when you blast it, the volume after blasting is significantly higher than before, and we call this process a bulking process that is illustrated in this Voronoi cartoon model, showing that the geometric fit of the individual blocks doesn't allow the rock mass to stay together and increases in volume. So if we want to support this type of rock, we have to find ways to deal with the volume increase that occurs as the rock is failing, and that means we need to design so we can survive the deformations imposed by this process of disintegration. To illustrate the relevance of the bulking process, here is an example of a stress-fractured rock mass above a vent door, and the opening of cracks and fractures in that rock mass led to half a meter or more of convergence in the center of this vent door. This is what I'm talking about, stress fracturing causing large deformations through an excavation. So in the written version, I explain why load, factors of safety, as well as energy and bursting conditions are not really most relevant for the design. We need to design against the deformation that stress-fractured rock brings, and for that we have to establish the depths of failure that I explained earlier. We then have to figure out what is the deformation demand, how much is this rock mass bulking, and what is the deformation capacity of the various support systems. Let me illustrate the process again by a numerical model here, where we have a pillar that is being loaded and strained, and we see typical stress fracturing as well as buckling mechanisms, and I'm sure many of you have seen that in the field. This is the image that I showed earlier, compact or massive rock being strained, stress fracturing, leading to a disintegrated rock mass. Where can it move to? Only to the right, into the excavation. So if we simulate that with a Voronoi model, we realize that any tangential straining is causing the radial deformation into the opening. This is a very important, simple fact, that if we do not cause tangential straining of stress-fractured rock, it won't move into the excavation. So when we look at an image like the one I introduced earlier in the presentation, and we ask ourselves, what was the problem? The first one is, oh, the support didn't work. No, in reality, that's not the case. The first axiom of deformation-based design is, if there is nothing driving the deformation, nothing would be happening. In this mining situation, it was that the pillar was not wide enough, we got excessive deformation, or that the cave control was not sufficient, we got excessive deformation, and it was that the driver of bulking was the source of the problem. No support would be adequate to stop that deformation. Other measures have to be taken by moving tunnels apart or making pillars wider or controlling the loading process if you want to prevent these type of failure processes. The first element, therefore, of deformation-based support design is to identify what are the sources of tangential straining of the excavation that deforms the bulking rock. The second axiom is that if you have a rock that wants to bulk up, increase in volume, because it is geometrically not possible to have these blocks move relative to each other, and we have a certain level of strain, we have to control the bulking process. On this diagram on the right, I'm showing the tangential strain against the overall bulking, and illustrate that after elastic behavior, we end up with a bulking that is significantly larger, or the deformation in the horizontal direction is significantly larger than the strain in the vertical direction. For 1% of strain in the vertical direction, we have 5% strain in the horizontal direction into the excavation. Therefore, the second axiom of deformation-based support design is to support it such that this bulking process can be reduced from, let's say, 5 to 1 to 1.2 or even better. And for that, we need to have reinforcements of the broken rock mass by yielding support that sustains the localized straining, as well as we have to provide confinement so that the broken rock cannot increase excessively in volume. Again, referring to the written version, I give some guidance on how we can anticipate the amount of bulking, and I illustrate here that it depends on the confining pressure, the pressure that the support is providing, but it also depends on how much tangential straining an excavation experiences. If we excavate a single tunnel, and have relatively limited strain because there is no other source of deformation. In this example, with a light support providing 0.1 megapascal of support, we would have about 2.5%, and if the depth of failure is 1 meter, we would have 25 millimeters of deformation due to bulking. If the same tunnel was in a mining situation where we add additional tangential straining of about 1 to 2%, the same tunnel would have, of course, a deeper depth of failure of, let's say, 2 meters. The bulking would be much more significant, and we would result or have 160 millimeters of deformation. Even if we support this tunnel with an unrealistically high confining pressure of 1 MPa that we can never achieve, we would still have in the order of 90 millimeters of deformation. The point that I like to make here is actually not how to exactly determine these values, but to point out that none of the numerical models that are conventionally used in support design take into account the bulking process and therefore the deformation that come from the bulking process. So in these examples, 25 to 160 millimeters of deformation is not taken into account when you use conventional continuum mechanics models in the design, and therefore the design that you're presented with or that you're presenting in the tender stage is clearly flawed. And a consequence of it is illustrated here on 2 examples where we have bulging of shotcrete and mesh because behind is a bulking rock mass that was not properly controlled. And this example may be much nicer. On the right side, the support was able to control and restrict the bulking process, but on the left side, it was incapable of stopping the bulking, and the bulking process destroyed the support. So in summary then, the goal of deformation-based support design in these rock conditions is that we have to first eliminate the drivers of the bulking, which is the tangential straining by whatever means you have available, and then secondly, control the bulking of the rock mass itself by reinforcement or by providing support pressure. To try and explain this process a little bit better, I use here an analog of a gabion. What do we do when we use a gabion in a retaining wall? We take broken rock and we retain it within a cage of steel. We reinforce it, therefore, across the gabions, and as a result apply some surface pressure to a slope behind. If we translate that into tunneling situations, the solution is that when we deal with stress-fractured rock, we have to generate a gabion-like support system consisting of bolts and retention systems that are able to stop the bulking process and therefore resist tangential straining in the vertical direction, as well as providing confinement to the rock mass behind it and therefore stopping the deepening of the stress fracturing process. So deformation-based design basically means to find or define what the deformations are and then select deformation-compatible support components, yielding bolts. And again, I give more details in the written version. We have to have a deformable retention system. If you have a shotcrete arch that is very stiff, the bulking process will self-destruct the support system, and we have to confine it by potentially adding debonded cables, cables that have enough give so the rock can fracture and expand. Let me end by just pointing out that some recent developments by Tasca I think are very promising so that we can capture this in the future. What you see here is a bonded block model in 3-deck that captures the stress fracturing process around the excavation and also shows support elements that are performing properly in this media and in this case illustrating that at the points where the blocks are separating, we have failures of stiff supports. If we support the same rock under the same condition with deformable debonded cables or yielding bolts, you see that the overall pattern of failure is not changed very much. The gray scale showing how much confinement there is on the excavation, but we see that the bolts are yielding, shown in red, but they're not failing because the yield deformation is distributed properly. So to analyze or predict in the future how support will behave, these type of technologies will be highly useful. Unfortunately, they're very computer challenging today and are not quite ready yet for three-dimensional conditions, but they will provide us with the fracture pattern, the yield deformation that occurs, the bolt forces, as well as the confinement contour that are relevant for pillar design questions. So let me conclude my presentation by simply saying that for economic and safe construction, it is important to anticipate the actual behavior of highly stressed rock. It has to be understood and documented during the tender stage so that we can anticipate the implications of stress fracturing, including the bulking process. Based on that, then a contractor can be presented with efficient and effective ground control measures, and these measures have to be flexible because of the variability of stress and strength along a tunnel. We'll never be able to predict exactly where this process is occurring, and so methods of excavation and support have to be compatible with the fact that the stress fracturing process leads to low stand-up times and bulking processes. We have to change our thinking in the design from load on steel sets, etc., to a management of deformations, and as I indicated earlier, that involves eliminating the driver of stress fracturing, particularly in mining situations, controlling the bulking process when the rock is stress fractured, and creating a self-supporting arch around the excavation as kind of described by the Gabian concept. So that brings us full circle to my introduction with my visit last week, which basically says that the challenges of managing highly stress-fractured rock is in building reliable arches around an excavation in a manner that cannot fall apart with low stand-up times. And it also brings me back to my first point. If the technical details were confusing you, my message is a project has to be designed so it can be built. And in stress-fractured ground, we have to take into account that stress fracturing is a major problem for the contractor, that we have to provide them with means to manage the low stand-up time issues. I'd like to end with acknowledging many that have contributed to the work, particularly from Rio Tinto, while I was working at the Rio Tinto Center for Underground Mine Construction, but also many of my colleagues that have been contributing to various parts of the work that I have presented today. Thank you for your attention, and thank you to all the research sponsors.
Thanks, Peter, for providing a very interesting and visionable lecture and describing to us the risk and suggestions for how to overcome it, and also giving us good examples to consider in our daily work. So, in appreciation of your contribution and of the lecture, I would like to give you this certificate of appreciation for my today. And then I will call upon Mike Smithson to come up.
Thank you, Peter. Thank you, Soren. Prior to us taking a quick break, I'm going to introduce Randy Essex, who was our program chair, and then we'll have a short break following that, and then Mike Mooney, who's our scientific committee chair, will speak a little bit about the conference. Randy Essex. Good morning. We're a little bit out of sequence, but what is our business all about but recovering? So we recover. I'd like to welcome you all to the 2016 World Tunnel Congress. Some thoughts about our technical program. Completing the technical program for this Congress has been a rather intense effort by a team of hardworking industry members, and I would like to give you some background about how we've gotten here today. Our team was led by 5 track chairs, 4 individuals and myself, and please, I'd like to acknowledge some people who've already been introduced, but they served as track chairs as well, and that's Amanda Elioff, Lonnie Jacobs, Mike Mooney, and Priscilla Nelson. So a round of applause for these 4 people. We're going to be having 5 concurrent technical sessions during this Congress, as well as a number of IT organizational meetings and workshops. So it's a very full technical program. The sessions will be led by 20 session chairs who represent a cross-section of our industry: owners, contractors, suppliers, and engineers. Can each of the session chairs please stand as I recognize you as your name is called, and please hold your applause until the end. Red Robinson, Erica Moonen, Brian Fulcher, Paul Schmall, John Riley, Ray Sterling, Brett Campbell, Allan Marr, David Caden, Greg Davidson, Matt Fowler, Mike Rispin, Matt Swinton, Brett Zernich, Matt Preedy, Jack Brockway, Vojta Gall, Colin Lawrence, Dennis Ofiara, and Les Bradshaw, a Class A team of people who have worked really, really hard to get us here today. Please. We had a rather daunting task. We had more than 720 abstracts. Each abstract was reviewed by at least 2 independent reviewers, in some cases 3 or 4. We screened these abstracts for quality of content as well as geographic representation. Eventually, 370 abstracts were approved for manuscript preparation. We then advanced to manuscript review. A scientific committee consisting of 100 technical experts from around the world was organized and led by Mike Mooney, our scientific committee chair, who you'll hear from after the break. Ratings and written comments were conveyed back to the authors, and initial manuscripts were revised and resubmitted and reevaluated. Lots of effort involved in all of these activities. In the end, we have 185 manuscripts that will be presented during the oral technical sessions, and about 160 accepted for poster presentation. You should have received 2 spiral pocket guides in your registration materials. The thicker guide contains the abstracts of all the papers being presented, as well as a WTC at a glance grid in fold-out form, and hopefully we have a visual of that product. It's in both of your guides, and it gives you a good sense of what's going to be happening during the Congress. There we go. There'll be a quiz in 5 minutes. Read it carefully. The thinner guide contains a calendar of events, information on the conference sponsors and exhibitors, venue maps, and also contains this critical foldout. On the back side of the foldout is a session at a glance summary. Now, this WTC glance shows all the functions that will be held during the Congress. Most of the events are here in the Moscone Center. Activities being held in the Marriott Marquis Hotel are noted on the WTC at a glance visual. The technical sessions will start this afternoon, will be held tomorrow afternoon, as well as Wednesday morning and Wednesday afternoon. The exhibit hall will open at lunch this afternoon and will be open on Tuesday and Wednesday, starting with the morning breaks. There are a number of other ITA-sponsored events and activities, including a BIM workshop and a Think Deep session on Tuesday afternoon. During the tactical sessions, we will be keeping strict control to time so that you as delegates will be able to move from session to session, knowing that presentations you want to hear will commence at the exact times that are shown in your pocket guide. Papers accepted for podium presentation will be displayed for the entire day on which their session occurs. They'll be displayed on the exhibit hall floor for the entire day. Authors will also be available between 1 and 2 p.m. during the lunch break to address any questions you delegates may have about their content. Posters will be rated by a review committee, and a prize will be awarded for the best poster on the day. One for Tuesday, one for today, and 2 on Wednesday because we've got 2 sessions. The 4 winners will be presented with a rather handsome gift card from Amazon. Good luck to all. The conference proceedings, including all papers presented in oral and poster form, are contained on a thumb drive that is included with your full registrations. You should have received a coupon in your registration packet that you can exchange for the thumb drive proceedings at the UCA of SME table just to the left of where you registered. Also included in your registration is a copy of a new book, The History of Tunneling in the United States, that will be mailed to you following the Congress. If you wish, you may also buy a hardcover version of the proceedings, also at the UCA table at an additional cost. The hard copy proceedings will be mailed to you to an address that you provide so that you won't have to worry about carrying heavy goods in your valises back overseas. A few words about what happens tomorrow morning. Tomorrow morning we will hold the ITA open session titled Industry Advances. The program will feature completed work products and ongoing activities of the ITA working groups and activity committees, which are really the heart and soul of this organization. An initial session will celebrate ITA reports that have been published in the last year, and then short presentations will be made by the animateurs of those completed works. The second part of the program will consist of more of an open dialogue and discussion on specific topics raised by selected working groups. Panelists, as well as the audience, will have the opportunity to comment on the key advances in industry concerns. The fundamental point is we want your input on where working groups are headed and what issues you think they should be addressing going into the future. It should be a good discussion, an engaging discussion, and we certainly welcome all of your contributions. On Wednesday, we're going to be holding our farewell cocktails reception and banquet. The program will feature 2 musical genres, a jazz ensemble during appetizers and dinner, followed by a tribute band called Catch a Wave. They look and sound just like the original Beach Boys, so we can look forward to some literal good vibrations. On Thursday, there will be a technical tour of the Central Muni Subway right here in Chinatown. And for those who would prefer to combine wine with tunnels, there is a trip to the wine caves in the Napa-Sonoma wine region. Either will be entertaining and informative. The pocket guides provide additional information on accompanying personal tours and activities in and around this great city by the bay. On behalf of the organizing committee, I wish you an informative and memorable Congress. And we'll take a break. And we'd like everyone to be back at 10:30 because we've got a very large number of musical professionals outside from my alma mater, University of California, Berkeley. So if we could take a break and start promptly at 10:30, thank you very much.